everyone, in this video we are going to discuss electric field. It is also known as electric field strength or also known as electric field intensity. It is denoted by a letter capital E. It's a vector E. It's a vector quantity. It has both magnitude and direction. Let us discuss about electrostatic force. What is electrostatic force? When you have two charges, like or unlike charges, there will be, and if you place them close to each other, there will be maybe a repulsion or attraction. Anyway, there is a force between them. Clear? It is a non-contact force. Non-contact force means because it is not necessary to have a physical contact between both the charges. Clear? So, but still there is a force of attraction or repulsion between them. There is a Coulomb's force. Okay, so in order to understand more about this force at a distance, we introduce the concept of electric field. Let us consider a point charge Q. So we have a point charge Q here, and if you bring any other charge, because a single charge cannot make a force on itself. Okay, so in order to experience a force, we need one more charge body or one more charge. So we are bringing a charge anywhere, you're keeping here or anywhere around this charge, there will be a force. If there is a force, that means the charge which I kept is in the field of this charge, in the electric field of this given charge. So in order to understand that charge, we need to bring a charge. We need to bring another charge. So I'm going to test the electric field of this point charge Q at a point here. So this is point P. I'm going to test the electric field at this point P. It is at a distance R. So now look at this. There is nothing. It's just a point. So in order to test this charge, I'm bringing a test charge. A test charge, and it is denoted by Q naught. So I brought it here and I place here this Q naught. So why I require this Q naught? Because unless we have another charge, we can't experience any other force. Clear? We can't experience any force. So we need a test charge. So it's a Q naught. It is a test charge for testing the electric field. So I brought it here. So there will be a force between them. Okay. So that force, according to Coulomb's, we have it is F is equal to, it is Q naught by R square. Okay. Now quantitatively, what is electric field at this point? It is the force experienced by. It is the force experienced by this test charge or per unit positive charge. So we can say that the basic equation of electric field is E is equal to the force experienced per test charge. I need to tell you something more about the test charge Q naught. Look at this Q naught. Okay, so I told you already what we call it, it's a test charge. It is, the purpose of this charge is to simply test the presence of electric field at this point. Okay, and this Q naught must be a very small charge so that it also have a field around it. And remember, this Q naught, the presence of Q naught should not make any disturbance to the electric field of this given charge. So remember, the Q naught, it should be very small. Okay, good. Now let's come to this formula. See, what is electric field? Quantitatively, we can say it is the force per charge or the force F by Q naught. Look at this equation. So what is its SI unit? SI unit, you can say that it is force by Q naught. So it is Newton, force Newton, and Coulomb, SI unit of charge is Coulomb. So it is Newton per Coulomb. It also has one more unit that you will study in the second chapter, that is volt per meter. Remember, these two are the SI unit of electric field. Okay. Now we can modify this equation. The electric field at this point P due to this charge Q is given by E is equal to F by Q naught. Now let us substitute the value of this F from above. So look at this. E is equal to the value, it is K Q Q naught divided by R square. So the value of F substituted divided by Q naught, divided by Q naught. So Q naught and Q naught cancel and its magnitude E is equal to K Q by R square. Clear? So this is the new equation of electric field. And also remember, what is K? K is a constant and its value is 1 by 4 pi epsilon naught. We know electric field is a vector quantity, and now we have seen its magnitude. Now the direction. Now the direction of electric field. Look at this diagram. Again the same situation. It's a point charge Q and test charge Q naught separated by a distance R. What will be the force between them? Force, the nature of the force between them. Both of them are positive, so it is clear that the force will be a repulsive force. So what is the action of Q on Q naught? It will be pushing Q naught in that direction. So the direction of force on Q naught due to Q will be this direction. So this is the direction of force. Clear? So remember, the direction of the force will be same as the direction of electric field. So remember, at this point the electric field will also be in the same direction. So electric field will also be in the same direction. So remember, the electric field has its direction same as the electric force at this point. Suppose if this charge is a negative charge, it's minus Q, and we have got a test charge Q naught over here, and now this is the distance. What will be the action between them? It will be attraction, because negative and positive, unlike charges, they attract. So the direction of force will be this. This is the direction of force. Clear? So what is the direction of force on this Q naught, positive test charge Q naught? The same will be the direction of electric field. So here the electric field will be in this direction. Okay, so this is the direction of electric field. We have seen the electric field due to a point charge at a point. So we have derived its value. E is equal to K Q by R square. Now, electric field due to a system of charges. We have n number of charges, Q1, Q2, Q3, etc. up to Qn. So many charges are there, and all these electric charges, they have their own electric field. And what will be the net electric field at a particular point P? So in the beginning, for our convenience, we are starting with two charges, Q1 and Q2. For example, here is our first charge. This is Q1, and the next charge is over here. It is Q2. So there will be a field due to Q1 and Q2, and we are going to find, let's consider the point P over here. So this is point P, okay, and where you put the test charge Q naught. The distance between Q1 and Q naught, or Q1 and P, it is R1P. Similarly, the distance between Q2 and Q naught is R2P. Okay, got it. Now, at this point P or on this charge Q naught, what will be the, at this, there will be a force due to Q1 and Q2, and all these three are positive, so the action will be repulsive force. Okay, so what will be the direction of force on Q naught due to Q1? It will be in this direction. So this will be the direction of force. This will be the direction of force. In the same way, what about Q2 and Q naught? The force on Q naught due to Q2 will be this direction. Okay, so we have seen the direction of the force on this positive Q naught will be the direction of electric field. Now let us discuss about this electric field. Electric field at point P due to the first charge Q1, let it be E1. So it's clear that this will be the direction of E1, so E1. What about the direction of E2? It means the electric field at point P due to the charge Q2. So it will be this direction. So this is the direction of E2. Now what will be the net electric field? Let us recall the vector addition law. You remember it? Yes, parallelogram law of vector addition. Let us complete a parallelogram. So this is a parallelogram, and the resultant of these two vectors E1 and E2 will be given by the diagonal. So this is the diagonal. So this is the net electric field E. Okay. Mathematically you can write that the value of this E, vector E, is the sum of vector E1 and vector E2. What will be the value of E1? E1 will be, look at this, E is equal to K cube by R square. So what will be E1? E1 is equal to, it is K Q1 divided by, what is the distance? R1P. So it will be R1P square. But I need the vector quantity, it is E1 vector. So here I write, it will be, there in RHS, it's R1P unit vector. What is R1P unit vector? It means the direction of force or electric field from Q1 to Q0. So this is the direction of R1P. It's a unit vector. The same way, in this direction, the unit vector will be R2P unit vector. Okay, so E1 value we have, and similarly, what will be the value of E2? E2 is equal to K Q2 divided by R2P square, and unit vector R2P. If there are n number of charges, okay, so what will be the net electric field at this point P? At present we have considered only two charges, they are Q1 and Q2. If there are Q3, Q4, etc. up to Qn, the net force will be, we have to consider each and every charge. So electric field of the third charge E3 plus the fourth charge E4 plus etc. plus etc. plus etc. up to the nth charge En. Okay. So we have to add all the values, and the net value electric field will be given by this equation. So what will be the E2? E1 and E2 I have already written. What will be the value of E3? E3 you can write on E3 is equal to, it is K Q3 divided by R3P square and R3P unit vector. What about the nth charge En? It will be K Q N divided by R N P square unit vector R N P. Correct? Now we are going to substitute the value of E1, E2, E3 and En in this equation. We have all those values, so that is E is equal to E1, it is K Q1 divided by R1P square R1P unit vector plus E2, it is K Q2 divided by R2P square R2P unit vector plus third E3 K Q3 divided by R3P square R3P unit vector plus etc. plus En, it is K Qn divided by Rnp square Rnp unit vector. So it's clear that the constant K is common everywhere. So you can write down that is K is common outside. So we can see, you can write it as K outside. So it is Q1 divided by R1P square and you can write it, finally you can write it like this, that is E is equal to K, this sigma, the entire bracket term you can write in summation form, that is sigma I is equal to 1 to N Q I divided by R I P square and unit vector R I P. And this equation will give you the net electric field at point P due to all the charges. According to the principle of superposition, the net charge at that point P due to all the other charges is the vector sum of individual electric field, and this is what we call the superposition principle.